All right, welcome to this video. Today we're going to learn about calculating the parameters of a milling operation. So we're going to calculate the spindle speed. So what is the spindle speed in RPM? What's the feed rate in inches per minute? Because most CNCs read feed rate in inches per minute for a milling operation. We want to figure out the material removal time in minutes and possibly seconds. And we'll figure out the material removal rate in inches cubed per minute. And then finally, our power requirements. Okay, so in this example, we're going to work with 61 T6 aluminum. So this block is made out of 61 T6 aluminum. It has a hardness of about 95 Brinell on the Brinell scale. We're going to use maybe a 1-inch cutter, so a pretty big cutter. So that'll be let's call this an HSS end mill. So that HSS is high-speed steel, and it's going to be it's going to have 4 flutes. Okay. So the cut that we want to make is 0.75. Maybe I'll get a pen and I'll draw the cut here on the part here. So it's got this is going to be it's going to have some sort of thickness, some sort of width, and some sort of it's going to be full length here. So we're going to cut out everything that you see in blue here. Okay, so it's going to have some sort of thickness. So we'll call that T. It's going to have some sort of width. And it's going to have some sort of length. So let's put some actual values to those. So let's say I'm just going to switch my pen color. So let's just say this is 0.1 inches deep by 0.75 inches in width, and let's say this is over the 6-inch block. So that defines our step in here. So then we're going to draw the cutter here. So we're going to do a climb milling operation, which means if the tool is rotating clockwise, it has to come in this direction. So here's our cutter. And it would be spinning in this direction. So it's going to come along here, and It's not gonna, it's 1 inch, so it's not gonna be full depth, and that way we can ensure that we get a clean edge on this side. So first, to calculate the spindle speed, I'm going to switch back to white here. I'm going to go to spindle speed. The formula that we use is similar to drilling. It's actually the same formula. So N equals 12V over pi d. Now we know what our diameter is. So our diameter is 1 inches. 1 inch. But we don't know V. And if you recall from previous videos, V was surface speed, which is in units of feet per minute. So I have this table here that I adapted from DeGarmo's material processes and manufacturing. So it says that aluminum alloys for a high-speed steel cutter, I'm just going to circle our value here, and for end mills, so this chart's got a lot of packed into it here. So it's got face mill, slab mill, end mills, full and half side mills, saws, and form mills. So we're going to use end mill, and we'll go down to aluminum. So it says we could mill anywhere between 300 and 1200 feet per minute. Now that's a pretty staggering difference. I guess you could cut 4 times faster if you go to the 1200 and the 300. So let's just imagine, like, this is quite a big cutter, a 1-inch cutter. So going fast would be pretty heavy duty on the machine. Maybe that would be a good exercise to see what the power difference is based on the spindle speed. But for our purposes, we'll just go through this exercise once. Maybe that's something that you could do for practice, is just change your surface speed. So this is our first time putting this step in, so I'm feeling a little bit conservative, so maybe we'll go around 400. So we'll just set that up as 400 feet per minute. All right, so we'll plug this in. So N equals 12 times 400 divided by pi times 1 inch. So let's calculate that now. So 12 times 400 divided by pi, and then divided by 1. Didn't really need to divide by 1, but that's how you would do the calculation. So our RPM is around 1528. So revolutions per minute. All right, so we'll just box that answer there. And now we're going to figure out our feed rate now. So feed rate. And so this is going to be in inches per minute. So for milling, F is equal to our spindle speed in RPM, feed per tooth times the number of teeth in lowercase n. So that's our spindle speed. This is our feed per tooth. And then this is the number of teeth on the end mill. So if you have a 2-tooth end mill, that would be 2. If you have a 4-tooth end mill, that would be 4. So we'll go up. We said that we wanted to use 4 flutes, a 4-fluted 1-inch high-speed steel end mill. Okay, so well, the only thing we don't know, we know the spindle speed, we know how many teeth we have, but we don't know the feed per tooth. So we have another table here, and now normally these tables would come from a brochure or a technical data sheet that would come with your cutter. But these are kind of just general numbers that we can use. They're from DeGarmo's Material and Processes in Manufacturing book. So I'll just switch to red pen here. And so again, we're using the high-speed steel cutter. It's an end mill, and we're using aluminum. So we can cut anywhere between 0.015 inches and 0.040 inches. So again, I'm feeling a little bit conservative, so why don't we just go with the smaller number, and we'll go at a little bit of a slower speed. So if you increase this number, your feed rate goes up. If you decrease this number, your feed rate goes down. So maybe I'll just draw that there. So if if any one of these parameters goes up, our feed rate goes up. If it goes down, the feed rate in inches per minute goes down. So let's choose 0.015. This is the first time I've milled this, so I'd rather be conservative than go too fast. So feed per tooth is going to equal to 0.015. Okay. So we're going to take our spindle speed, 1528 times 0.015 times 4 for the number of teeth that we have. And that's equal to 1528 times 0.015 times 4. And so we can go pretty quick, actually. So that's 91.8 inches per minute. So that's pretty fast cut, I must say. 91 feet. Trying to put that in relative terms. 92 feet, I think, is 8 feet. Or sorry, 91 inches per minute. So 92 inches is 8 feet. So in 1 minute, it would move 8 feet. So it's while that may seem like a slow walking speed, it's quite a fast cutting speed. To put it into relative terms. Okay, so now we wanted to figure out our material removal time. So to do that, basically, you're asking yourself, how long does it take for the cutter to move from one side of the block to the other? So what's involved in that is the length of the block and how fast it's moving. So how fast is your feed rate, and how long is the cut? So let's kind of just dissect that formula. So this is going to be material removal time. MRT is equal to, and we want minutes as our unit, so it's going to be our length of the cut divided by the feed rate in inches per minute. So this is in inches, and this is in inches per minute. So these would cancel. And then the minutes would go on top. So that would be like 1 over minute after these cancels. And so that goes on top. So that's how we get minutes as our unit. So 6 inches divided by 91.8. So this isn't actually going to take all too long, is it? So go to our calculator here. So I made a little bit of an error here. So this is actually supposed to be a 7. So 91.7, and then here 91.7. Okay. So 6 divided by 91.7 is equal to 0.6, and I don't want to make a mistake. So 0.065 minutes. And that's roughly equal, should be easy, maybe 1.2 seconds, so, or 1 second maybe. Let's see, there's 60 seconds in a minute, so I gotta multiply that by 60. Not even close. 3.9 seconds. Yeah, 6 times 6 is 36, so yeah. My mental math is not great at the moment. Okay, so 3.9 seconds there. So that's good. It won't take too long to mill that across. So now we'll figure out our material removal rate. So MRR is equal to, now we have to do a little bit of math here. We have to put some things together. So we want units in inch per cube. So basically we have to calculate how much material is gone, so the volume of this material, in the time that it takes to cut it. So we know T, we know W, we know L, and we also know how long it takes to cut it. So basically we can get volume over the time. So MRT. So volume is fairly easy calculation. That's our length times our width times our thickness over MRT. And MRT is actually L over F. So again, we can kind of do some things here where we could just plug this number into here. But we could also practice breaking this down, so and getting this as simple as possible. So L's would cancel, right? And then, much like how the minutes go on top of in the numerator, the F would go on the numerator because it's in the denominator of the denominator, which is in the numerator. So we'll stick the F up here. So then we can say that MRR is equal to F in inches per minute times W, our width of the cut, times T. Now, we didn't make a full cut with the cutter, so it's not 1 inch, it's 0.75 and it's 0.1 inch down. So take this, so our feed rate is 91.7 inches per minute. times the width, which is 0.75 inches, times the thickness, which is 0.1 inches. So an inch times an inch times an inch is inches cubed. And a minute, nothing else there, so we'll have to divide it by minutes. So our units work out, so we know that this formula that we created works. So now let's just plug it in. My screen moved over, I'll just fix that up. Okay. So 91.7 times 0.75 times 0.1 equals 6.88 inches cubed per minute. So now that we have our material removal rate, we can calculate our power. So how much power, what size of motor, and what sort of power supply do you need to feed this machine? So power is equal to our unit power times our MRR. So we have this table over here, and I've created a kind of a worksheet where you can see these tables for milling, and you can use these tables to practice solving your own equations. So aluminum with a 95 Brinell hardness is a unit horsepower of around 0.25 horsepower per inch cube per minute. So this is going to be 0.25 times 6.88. All right, 6.88 times 0.25. Wow, okay, so we need 1.72 horsepower. Okay, now I remember how many watts are in a horsepower, so it's times 745. So we would need roughly, what was it, 1281 watts. All right, so that's a fairly large number, so this is really hogging it out at quite a rate. You might see the lights dim with this one. Probably not. But speaking of lights, how many 60-watt incandescent lights is this? Well, we'll just divide it by 60. So that's roughly the same power to charge or to operate 21 60-watt lights. So not too bad. So anyway, that concludes milling parameters and the calculation of milling parameters. So we'll see you in the next video.